Okay, the next video for chapter 14 is on the ideal gas law. If you remember when we looked at the combined gas law last time, one of the things that we said that was the same every time was the number of moles of gas. And in this one, we're not necessarily changing the volume or the temperature or the pressure, but what we are is factoring in the number of moles of gas. The ideal gas law is based off of Avogadro's principle or Avogadro's law, which we've sort of already looked at. Avogadro's principle says equal volumes of gases at the same temperature and pressure contain equal number of particles or equal number of moles of gas. So when we were doing our mole conversions back in chapter 10 maybe, and we first learned that when you have 1 mole of gas, right, this would be 1 mole of gas at 0 degrees Celsius and 1 atm, this was what we called STP. We said that the volume, we used more significant figures. We said 22.414 liters. And that's interesting because it's independent of the identity of the gas. You can see that helium gas and nitrogen gas and methane gas all have the same volume when there's 1 mole. Okay, but so now what we're going to do a little bit differently is that we're going to put this in a different formula. It's called the ideal gas law, and it's PV equals nRT. Lots of variables in this, but they're variables that you know. Of course, P stands for pressure. And pressure could be in atm. It could be in millimeters of mercury, which is also called a torr, or it could be in kilopascals. Volume. Volume is, of course, V. But one thing is that it must be liters. It can't be milliliters. So if it's in milliliters, you need to change it to liters. N. This is a variable that we have not seen before, but N stands for number of moles, right? Think of, we can't have it be lowercase m because that would be mass. R is going to be something that we call over here, that's the gas constant. More on that in one moment. And then, of course, T is temperature, and that must be in Kelvin. Again, whenever we're using temperature in a formula, we need to use it in Kelvin. So now let's talk about this weird thing called the gas constant, this R. If you think about a formula, both sides of the equal sign need to be equal, including the units. And so if you just look at the things that we have units for, pressure might be in atm, volume might be in liters, R would be in number of moles, and temperature would be in Kelvin. So those units are not the same on both sides. And what R does is it makes sure that the units are the same on both sides and make sure that these work out. If you want to know more about this, Google derivation of the gas constant, derivation of R, and you can see how it is derived basically from numbers like that up there. So what is it? These are numbers that, you're not going to have a test on this, but if you're going to have a test on this, it would be on the test. So what is R? It all depends on what the unit of pressure is. So if the pressure is in atm, R is equal to 0.0821. And these have a lot of units. Ready? Liter times atm over mole times Kelvin. Those are the units of that number. They're not variables to be plugged in. Think about what I'm saying, that if these are the units, let me plug them in, right? I would plug this in for R, so that would be liters times atm over mole times Kelvin, and then look at what happens to the units, right? Now liters times atm are on both sides. Okay, what if it's in millimeters of mercury, which is the same thing as a torr? It is 62.36 liters times millimeters of mercury over moles times Kelvin. And if it's in kPa, it's 8.314 liters times kPa over mole dot K. So keep those numbers handy, write them on like a Post-it note or something, because you're going to use them for your homework problems and for the rest of these problems. But basically, these are formula problems now. We're going to use that formula. So number 9, what is the pressure in ATM? It's my circle to do. Will 36.0 moles of helium gas be if it has a volume of 45.6 liters at 45 degrees Celsius? Right? We write the formula. PV equals nRT. Pressure is what I don't know. Volume is 45.6 liters. The number of moles of gas is 36.0 moles. Which R am I going to use? Well, the question says I need my pressure in ATM, so I'm going to use the R that corresponds with ATM, so 0.0821 liters times ATM over moles times Kelvin. And then we need to put our temperature in there, right? So 45 plus 273 is 318 Kelvin. Ooh. Sorry about that, guys. Okay, and now divide both sides by 45.6 liters. And my pressure is equal to, look at how all these crazy units are going to cancel out. Mole in the numerator, mole in the denominator. Kelvin in the denominator, Kelvin in the numerator, liter in the numerator, liter in the denominator. So my answer will have units in ATM. It's 20.6 ATM. And yep, 3 significant figures is just fine, right? All of these numbers have 3 significant figures in them. Try number 10 on your own. Pause, try number 10, and then come back to it, right? What temperature in degrees Celsius does 65.6 gram sample of CH4 need to be held at to have a pressure of 1,000 millimeters of mercury in a 75.0 liter container? Right, the formula, PV equals nRT. What's my pressure? 1,000 decimal point millimeters of mercury. What's my volume? 75.0 liters. What's my number of moles? I don't know that right now, but I know that 65.6 grams is the gas in there, and that it's methane gas, CH4. And I can convert that to moles. 1 mole is 16.042 grams of CH4, and that equals 4.089. So that's my N, 4.089 moles. My R, because it's millimeters of mercury, I go back up to the table up above, 62.36 liters times millimeters of mercury over moles times Kelvin, and then temperature, right, is what I'm trying to solve for here. So now I just divide both sides by 4.89 times 62.36. So I'll do this 4.089, 62.36 liters times millimeters of mercury over moles times Kelvin. And you do the same thing on the other side. And you don't need to necessarily write this out all the time, but I wanted to show you, again, how these units cancel out. Millimeters of mercury in the numerator, millimeters of mercury in the denominator. Liters cancel, moles cancel. And then I have Kelvin. Kelvin in the denominator of the denominator is the same as being in the numerator. 3 significant figures for all of these, right? This is 3, this is 3, this is 4. So my answer comes out to be 294 Kelvin. The question did ask for in degrees Celsius. So I subtract 273 to get 21 degrees Celsius. I don't need to make that 3 significant figures because my last step was subtraction, right? Subtraction is just number of decimal places. Okay? Try number 11 here, right? Feel free to press pause and then come back to number 11 after you have it done. If the pressure exerted by a gas at 37 degrees Celsius in a volume of 1.84 liters is 94.7 kilopascals. How many moles of that gas are present? And then if the gas is ammonia, how many grams are present? PV equals nRT, right? One thing that we didn't talk about, how do I know when to use this formula? This formula, nothing is changing. Notice in the problem, there's no new volume, new pressure, new temperature. That's when you would use Boyles-Charles, Gay-Lussac's, or the combined gas law. This also has moles in it. None of those previous questions had moles in it. So plug in what I know, which is kind of a lot here. I know that the pressure is 94.7 kilopascals. I know that the volume is 1.84 liters. I don't know the number of moles. I know I'm going to use 8.314 liters times kPa over moles times Kelvin. And the temperature is going to be 37 plus 273 or 310 Kelvin. Right? Divide both sides by 8.314 times 310, and we get the number of moles of being 0.0676 moles. Okay, and the second half of the question says, if it's ammonia, how many grams would that be? Right? Well, then I would just take that and I would convert it to moles. 1 mole of ammonia has a molar mass of 17.034 grams. And then again, 3 significant figures, 1.15 grams of NH3, right? Either one of those two numbers is my answer. So now what we're going to do is we're going to combine. We're going to combine two of the laws here. We're going to combine the ideal gas law, and we're going to combine the formula for molar mass. Remember the formula for molar mass, or what is molar mass? That's the number. That is the formula for the number of grams in 1 mole. And so the number of moles, so N would be the number of moles, that would be M, which is the mass, over what would be molar mass, the number off the periodic table. When we type it, it looks like a capital M, but usually it actually kind of looks more like this weird scripty M. So if you see it in your textbook, it may be written like that. The units do cancel out. This would be, the top would be grams. Molar mass from the periodic table is grams per mole. When you divide by a fraction, it's like multiplying by the reciprocal. So grams times moles over gram, right? That equals moles. That's what N is equal to. So look at these two formulas. I'm going to basically substitute the N. Think of like what you have done in math class when you solve a system of equations by substitution. So combine the equations and solve for molar mass. So I would do PV equals, instead of N, I would do mass over molar mass, RT, and now solve for molar mass. So I would multiply both sides by molar mass, divide by, so I'll actually do that out because a lot of students have difficulty, following the algebra here. And then in the next step, I would divide both sides by PV. So the formula that I'm going to wind up with, right, because these guys would cancel out, would be molar mass is equal to M, the mass, R, the gas constant, T, the temperature in Kelvin, over pressure times volume. And so if you get a question that says, what is the molar mass? And you have mass and all the other stuff, you can use that formula. But one interesting thing that sort of comes out here is that we have mass in the numerator and we have volume in the denominator. And mass per volume, you know what that is? Density. So I'm going to just retake that formula. Molar mass is equal, and instead of the M and the V, I'm just going to substitute a capital D for density. That would be density times RT over P, or, right, density is equal to molar mass times the pressure over the gas constant times the temperature. So again, depending on what the question asks, these two formulas, which are what we would call derived formulas, right? These aren't like new information. All they are is algebraic manipulations of formulas that we already have. But they're going to allow us to do some problems a little bit easier. So number 12 says, what is the molar mass of a gas if 75.0 grams of the gas has a volume of 475 liters and a pressure of 960.6 millimeters of mercury at 120 degrees Celsius? So the question's asking for molar mass. So I could do this one of two ways. Molar mass is mass over the number of moles. Okay, grams per mole, right? So I could find M, I could find N, and I could divide those. Or I could use this formula, molar mass equals MRT over PV. What is the mass? 75.0 grams. What is the R? Because my pressure is going to be in millimeters of mercury, it's 62.36 liters times millimeters of mercury over moles times Kelvin. And then the temperature, 120 plus 273 is 393 Kelvin. What is the pressure? 790.6 millimeters of mercury. And then what was the volume? That's 475 liters, right? Look at how all these units cancel out. Millimeters of mercury cancel, liters cancel, Kelvin cancel. So what are you left with? Well, mathematically, I'm left with the number 4.89 gram on the top, mole on the bottom. And yep, that's the right unit for a molar mass, a gram per mole. How many grams are there in 1 mole? Okay, a few more problems using those formulas there. What is the density of fluorine gas at a pressure of 0.987 atm and 25 degrees Celsius? So you could use density equals mass per volume. You don't really have a lot of information to use that formula though. If you use that formula, you need to sort of assume how much you have. You could assume 1 mole and then find the mass that way. And you could find the volume of 1 mole of gas and then divide those two. Or you could just use the formula that we derived on the previous page. Density equals molar mass times the pressure over the gas constant times the temperature. What is the molar mass of fluorine gas? 38.00 grams per mole. What is the pressure? 0.987 atm. What is the gas constant? 0.0821 liters times atm over moles times Kelvin. And what is the temperature? 25 plus 273 is 298 Kelvin. Right? Look at how nice the units cancel out. ATM, ATM, Kelvin, Kelvin, mole, mole. So what are the units here? The units are, well, my number comes out to be just 1.53. And then the units are gram in the numerator, liter in the denominator, and oftentimes we use units of density as like grams per milliliter or grams per centimeter cubed, but all it needs to be is a mass or volume. So that works out perfectly. And then just the last question, if a sample of oxygen gas has a density of 2.66 grams per liter at 36 degrees Celsius, what pressure must the gas be at? So again, the question gives me a density. So density equals molar mass times pressure over R times T. There's other ways that you can answer this question by, again, assuming a 1 mole. You could go and figure out, because we know we could use all the other formulas that we know, like density equals mass over volume, or PV equals nRT, but this is putting them all into one. So what is the molar mass? 32.00 grams per mole, because we know it's oxygen. Oh, here, let me actually start with rewriting the density. The density is 2.66 grams per liter. The molar mass is 32.00 grams per mole. The pressure is what I want to solve for. The gas constant, it asks, oh, see, this pressure doesn't tell me what unit it needs to be in. So any one unit would be right. I usually do 0.0821. It's the one that goes with ATM, and ATM is the unit most used in chemistry. And then the temperature is 36 plus 273, or 309 Kelvin. Right? Solve. So multiply both sides by 0.0821 times 309 Kelvin. Divide both sides by 32 grams per mole. Look at all the units that cancel out. I can actually cancel out the units before I do any math. Gram on either side of the equal sign. Right? Liter on equal sign, on either side of the equal sign. Moles cancel, kelvins cancel. So yeah, my pressure will be an ATM to 3 significant figures, 2.11 ATM, right? Every number that we use here has 3 significant figures, at least, right? My molar mass has 4, okay? So there's lots of different ways to do questions like numbers 12, 13, and 14, but I like using those formulas that we derived. So the homework that corresponds to this is numbers 44 through 52, okay?